This is the test bed or the working prototype demonstrating the advanced driver assistance systems using MEMS-based inertial measurement unit for the Texas Instruments Analog Design Contest 2010. As you can see, all the electronics have been mounted on the thermocom. Now, the TI components that we have used are the LM3S2965 evaluation board, the CC2510 wireless system on chip, and the L293D motor driver. The other components that we have used are the BMA 183 axis accelerometer, the ITG 3200 3-axis gyroscope, the L298N motor driver, an electronic buzzer, and a few indicating LEDs. Now, the BMA 180 accelerometer is connected to the LM3S2965 evaluation board to the SPI interface, and the ITG 3200 is connected to the I2C interface. The car is propelled by DC motors. As you can see, there are two DC motors over here which propel the car backward and forward, and the direction of the car is controlled by the DC motor for controlling the drive shaft. As you can see, this is the steering pad used to control the direction of the car. Here you can see the BMA 183 axis accelerometer, and here is the CC2510 wireless system on chip. And these two buttons are used to control the car basically for moving it in the forward and reverse direction. So the tilt direct data is sent wirelessly through the CC2510 present on the steering pad to the CC2510 present in the car.
An active suspension features lowering of suspension based on vehicle velocity, thereby reducing chances of rollover. The control objective of the active suspension system is to reduce ground clearance as speed increases. This control is achieved by gathering the velocity data by integrating the acceleration along the x-axis from the 6 degree of freedom IMU. As you can see in this video, initially the upper LED glows indicating a higher ground clearance, but as the speed and velocity increases, the suspension goes down indicating a lower ground clearance. One of the most popular ways to steal a car is to simply tow it away. In response to this threat, many automakers, particularly European manufacturers, included anti-theft systems incorporating fluid tilt sensors. Large electrolytic fluid tilt sensors have the required sensitivity for this application, but they fall short in many other areas. Their tilt range is limited, so it's not possible to park a car at an inclination that is greater than the sensor can tolerate. In addition, fluid tilt sensors don't perform well in the widely varying automotive temperature environment. These shortcomings can be overcome by using a 3-axis MEMS accelerometer in the IMU for tilt detection. Another interesting feature that can be incorporated is triggering of an anti-theft alarm when the car is electronically locked and is moved about any of its axis beyond a particular threshold value. The gyroscope and accelerometer present in the IMU can be used to detect pitch, roll, and vibration. As you see in this video, when the car is tilted beyond a particular value, the buzzer present on the car beeps. Now we are going to demonstrate the drive-by-wire. The drive-by-wire technology could change the way people drive. A car with this type of system would rely mainly on electronics to control the steering. Conventionally, cars mainly use the hydraulic and mechanical technology for steering the vehicle, and although these systems are powerful, they can become very complex, inefficient, and conducive to wear and tear over the years. Our approach requires an accelerometer sensor to be embedded in the steering wheel of a car, and based on the magnitude and direction of tilt of the sensor, the drive shaft of the car can be controlled automatically accordingly. Now, as you can see, the tilt information from the steering wheel is sent wirelessly to the car, and based on the direction and magnitude of tilt, the drive shaft in the car turns accordingly and the car can be controlled wirelessly. Few vehicles have rollover detection systems, but automakers are trying to adopt this feature. This is particularly true for vans, pickup trucks and sport utility vehicles, which are more likely to roll over because of their higher center of gravity. These systems read the roll angle and roll rate of the vehicle to determine if it is tipping over. If it is, the system fires the side airbags to protect the occupants. The same rollover detection system can be implemented by using the 3-axis gyroscope present in the IMU, which can read the roll rate. Large roll angles can be encountered while traveling on bank curves with no possibility of rollover. Hence, we are using this accelerometer and gyroscope combination to detect the rollover. And here you can see the buzzer beeping, which is equal to the side bag airbags deploying. As you can see now in this video, the car is tilted slightly, which is equal to traveling on a banked road. But this will not trigger the alarm or side airbags being deployed. But when there is a sudden change in tilt, a rapid change in tilt, the buzzer beeps, and this is equivalent to side airbags being deployed. The hill start assist is used when starting a vehicle from the top on a hill by maintaining the same level of brake pressure the driver applied for a short period of time after the foot has been removed from the brake pedal. The system will release the brake pedal in proportion to the time elapsed or to the amount of throttle applied or until engagement of half clutch. The 3-axis accelerometer in the IMU will determine the inclination, the direction of inclination and whether the car is at rest or not by finding the velocity. So as you can see in this video, the car is moving backward, but the minute the IMU senses the car moving backward, brake is applied, and till engagement of half clutch or still a preset amount of time, the brake is applied, and after that the car propels forward. Hill descent control. This system allows a smooth and controlled hill descent on rough or slippery terrain without the driver needing to touch the brake pedal. As you can see in this video, without the hill descent control system, the car travels down rapidly and the driver must constantly push the brake pedal to maintain control of speed of the car. With the hill descent control system, the car moves at a constant speed, thereby making it easier for the driver to negotiate steep downgrade. Normally, cars have their headlights focused in one particular direction, and so while traveling on curves, the lights are focused away from the road, and hence they cannot see the incoming cars, which becomes very dangerous while traveling in curves. So this new headlight leveling system takes the tilt information from the accelerometer embedded steering wheel, and based on the magnitude and direction of tilt, the headlights are focused on the road accordingly by changing their position.